Consider this relation called the identity relation that we defined in the previous video to prove something, which is defined as the set of all a, b, and a2 such that a is equal to b. You can see for yourself that this relation is reflexive, symmetric, and transitive. Relations with those three properties come up quite often in mathematics, and we're going to explore relations with those properties in this video. In fact, a relation with those three properties is called an equivalence relation. To define what an equivalence relation is, we first let R be a relation on any set A and say that R is an equivalence relation if and only if R is reflexive, symmetric, and transitive. And these three properties should look or should sound really similar to you because they are, because these are the three properties of equality: the reflexive property, symmetric property, and transitive property of equality. And this is the case because equality is one of the big motivations for defining an equivalence relation at all and defining it in this way. You might also notice that this looks similar to the definition for an ordering relation, but instead of it being anti-symmetric, it's symmetric. So for example, if we let T be the set of all triangles and we define C to be this relation, let's call it the congruence relation, that where it pairs two triangles that are congruent to each other. And by the three properties of congruency, it's trivial that C here is an equivalence relation, because congruency itself is reflexive, symmetric, and transitive. As another example, if we let P be the set of all people and B be this relation that pairs two people that have the same birthday based on this statement that I defined, then we could show that B is actually an equivalence relation, because obviously everyone has the same birthday as themselves, and if A has the same birthday as B, then obviously B has the same birthday as A, so B is also symmetric. And also, if X has the same birthday as Y, and Y has the same birthday as Z, then X has the same birthday as Z, so this is also transitive, thus making B an equivalence relation. It might be helpful to look at this relation B a little more closely. We can think of this relation as splitting up the set of all people into 365 categories, right? One for each day. And then two elements of P, A and B, are B related to each other if and only if they exist in the same category. So for example, A and B here are B related to each other because A and B are both in the category January 1st. But they cannot be B related to each other if they exist in two different categories. That's what B does. It just pairs up elements that are in the same category. We could think of these categories in P as forming a family of subsets of P, in which actually we could form an indexed family as follows. So if we define D for days as, every day from January 1st to December 31st, wow, I almost forgot. Next, for any small d and big D, now for any R in D, let P sub R be the set of all P in the set of all people, such that P was born on R. So you can think of, like for example, P January 1st being the set of all people born on January 1st. Then if we let F be the set of all PR such that R is in D, then F forms a set of subsets of P. The elements of F are called the equivalence classes for the relation B, and every person in the set of all people exists in exactly one set in F here. Since you can only have one birthday. We can think of B as pairing each person in P to each other based on if they're in the same equivalence class. And again, we can think of B as pairing two elements in P that exist in the same equivalence class. And when writing it out, you can show that B is actually equivalent to the union for R and D of PR squared, where PR is obviously, again, the set of all people that have the birthday R. We will call f a partition of P because it splits P into disjoint parts. And it actually turns out that every equivalence relation on a set A determines a partition of A whose elements are the equivalence classes for that equivalence relation. But to show why this is true, we must first define even what an equivalence class and what a partition even is. To define these terms, we first assume that A is a set and F is a subset of the power set of A. Or in other words, it's just a collection of subsets of A. We say that F is pairwise disjoint if and only if all pairs of distinct elements of F are disjoint, and that F is a partition of A if and only if it satisfies these three conditions, where the union of F is equal to the set of A, or not the set of A, just A. 2, that F must be pairwise disjoint, and 3, that no set in F is empty. So for example, if we define A to be this and F to be this, then we could call F a partition of A because first of all, its union is 1, 2, 3, 4, which is A. We can see that no two elements have any common elements between them, so that satisfies the second condition. And clearly, no empty set is in here, so we could call F a partition of A. But for example, if we let F be this, then it is no longer a partition of A because it doesn't satisfy the second condition anymore because these two sets have 1 in common. For our third definition, we let R be an equivalence relation on A and X be in A. We define the equivalence class of X with respect to R being denoted as this, which is a set of all Y in A such that Y is R related to X. Or you could define it as X related to R related to Y. It doesn't really matter because again, R is symmetric. And then we define the set of all equivalence classes for A to be called A modulo R, which is denoted as I forgot if this is this a bat? I think this is a bat / I think. Not to be confused with A not R. The set, just wanted to point that out just for confusion. So if we define it as that, we can get this equality over here, where A modulo R is just the set of all equivalence classes for X in A. So in the case of this same birthday example we did earlier with this relation B, then the equivalence class for any person P in the set of all humans would be the set of all Q and P such that Q has the same birthday as P. So for example, if we have James here, whose birthday is January 1st, then his equivalence class with respect to B would be, the set of all people whose birthday is January 1st. And in the notation we did earlier, I removed it, but this set, the equivalence class for James would just be PR, where R is equal to January 1st. And in fact, we can generalize this further to say that the equivalence class for P with respect to B, for any person P, would be just PR in the notation we introduced earlier, where, R is P's birthday. So that just confirms that this notation we introduced earlier is an equivalence class. And just for a last example, let's let S be the set of all A, B, and R2 such that A minus B is an integer. So for example, 3.14 would be S related to 2.14, since 3.14 minus 2.14 is 1, which is an integer. But it is not the case that 3.14 is S related to 2.72, since that minus that is not an integer. So clearly, for any X in the real numbers, X is S related to X, since X minus X is 0, which is an integer, so S is reflexive. And if we let K be an integer such that A minus B is K for any two real numbers A and B, then B minus A is minus A minus B, which is minus K. So this means that if A is S related to B, then b is s related to a, which means it's symmetric too. And if we let a minus b be an integer k and b minus c be an integer m, then we can add these two quantities to get this, which simplifies to a minus c. And since this is just k plus m, which is an integer, then that means s is also transitive, which also means, of course, s is an equivalence relation. Well, what are the equivalence classes of this relation look like? Well, for example, the equivalence class for 3.14 with respect to s would be every real number whose decimal expansion starts or just is 0.14. In other words, the equivalence class for, let's say, whatever 0.73, this isn't a negative, by the way. It's just to represent like any real number that isn't a decimal. Any integer is the dash. So any integer 0.73, its equivalence class will only contain all integers 0.73. And in general, the equivalence class for x with respect to s will just only contain all real numbers that differ by x by an integer amount. And it goes with negative integers too, obviously. So if we choose some real number x in the equivalence class of, let's say, 3.14, then the class of x will automatically be equal to the class of 3.14. But if x is not in the class of 3.14, then this is not the case. And we actually do a more general proof of this later in the video, but just stay tuned for that. So for example, the class of 2.14 will be equal to the class of 3.14 since 2.14 is in the class of 3.14, but the class of 2.15 will not be the same as the class of 3.14 since 2.15 is not in the class of 3.14. And actually, since 2.15's class will only consist of real numbers that end with a 0.5 or 0.15, we can see that the class of 2.15 is actually disjoint from the class of 3.14, since the class of 3.14 would be consisting of all real numbers that end with a 0.14, which is not anything in this set. And in fact, we can see that for any two real numbers x and y, that their equivalence classes will either be identical or disjoint. And since for any real number x, x is in its own equivalence class, so this means that no equivalence class for any real number with respect to s is empty. And any real number will have exactly one equivalence class, or in other words, r modulo s is a partition of r, since what I just did there was show that r modulo s satisfies these three conditions to be a partition of s. And in fact, this can be generalized to say that a set of equivalence classes determined by an equivalence relation will always be a partition of that set that has a relation on it. And here I've just written that down as a general theorem. The proof for this theorem will be easier to understand if we have a couple lemmas. So this first lemma will say that if R is an equivalence relation on a set A, then 1, for all x in A, x is in its own equivalence class, and 2, for all x and y in A, y is in the class of x if and only if the class of y is equal to the class of x. The proof for the first property is rather simple. We just let x be an arbitrary element of A, then since R is reflexive, x is R related to x, and by definition of the class of x, here, since x is R related to x, then x is in its own equivalence class. And for the second proof, we assume that x and y are both in A arbitrarily, since of course it's a universal statement. Since it's an if and only if statement, we prove that if this is true, then this is true, and then we prove if this is true, then this is true. And since two sets being equal is also an if and only if statement, we do that too. So for the left to right implication, we first assume that y is in the class of x. Then by definition of the class of x, y is R related to x. So if we let z be in the class of y, then z is R related to y. And since R is transitive and this is true, then it's also true that z is R related to x, meaning that by definition, z is in the class of x. So for the right to left implication of the two sets being equal here, we let Z be in the class of X. Then by definition, again, Z's are related to X. Since R is symmetric, we already know that Y's are related to X, so it must be the case that X's are related to Y. And again, R is transitive, and this is true, so Z must be R related to Y. So Z is in, that looks like an E. So Z, I'll just remove it. So Z is in the class of Y. Now for the right to left implication of this if and only if, we first assume, this part is really easy. We first assume that the class of Y is equal to the class of X. Then since Y is in the class of Y, then Y is also in the class of X since they're equal. So that implies this, meaning we have completed the if and only if proof. I also forgot, you must add the little box at the end. So now, since we have this lemma, we can now prove theorem 4. Now, using this lemma to prove theorem 4, which said that if R is an equivalence relation on A, then A modulo R is a partition on A, then we have to show that A modulo R satisfies these these three conditions. For the first one, the union of A modulo R is equal to A. This is also an if and only if statement. So first we must prove that the union is a subset of A, and then that A is a subset of the union. So first we know that A modulo R only contains all equivalence classes of all elements of A. So by this definition, the union of A modulo R is the union for X in A of the equivalence class of X. Then we note that all equivalence classes for A are subsets of A, so it's obvious that the union of all the equivalence classes is going to be a subset of A too. Now to prove right to left, we first have to suppose that X is an A. Then, by reflexivity, X is in its own class, and the class of X is an A modulo R, so by definition of union, X is in the union of A modulo R. And since X is arbitrary, this means that A is a subset of the union of A modulo R. This makes A equal to the union of A modulo R. So for the second one, we have to show that A modulo R is pairwise disjoint. So first we assume that X and Y are equivalence classes, and X is an X and Y is Y. And this is important, X is not equal to Y. Lemma 5 says an element of Y is an X if and only if X is equal to Y, which is obviously not the case because we assume that X is not equal to Y. So by contradiction, I guess, it's contradiction. X and Y have no common elements, and since X and Y are arbitrary elements of A mod R, then you could say that A modulo R is pairwise disjoint by definition. Now this third proof is simple, and we're just showing that all sets in A modulo R are non-empty. So first we know that by definition A modulo R only contains equivalence classes of elements of A. For any X in A, the class of X is in A modulo R, and since X is always in its own class, then no equivalence class is empty. So this means that no set in A modulo R is empty. So by those three conditions, we can conclude that A modulo R is a partition of A. This theorem says that if R is an equivalence relation on A, then A modulo R is a partition on A. Well, in fact, every partition of A arises in this way. And that's demonstrated in this theorem, which says that if A is a set and F is a partition of A, then there exists an equivalence relation R on A such that A modulo R is F. To prove this, again, we need some lemmas. Since the conclusion of this theorem is an existential statement, we should try to, find R depending on the F that's chosen, since it seems like for different F, you would get, you would need different R's that make A modulo R equal to F. One way we could find some R depending on some F is to backtrack of how we even defined equivalence classes in this same birthday example. Here in the same birthday example, we said that B is an equivalence relation that pairs two elements of P that are in the same equivalence class. So for this, we should make a relation R that pairs two elements, or that pairs any two elements of A that are in the same set in the partition F. So for example, in the same birthday example, we did that by rewriting B as the union for R and D of PR squared, and that suggests on how we should define R, which would be the union for X and F of X squared. Now again, this would be a relation that pairs two elements of A based on if they're in the same set in the partition F, which is basically just what an equivalence relation does. So for example, if we let A be the set of 1, 2, 3, and I forgot to put an equal sign here for some reason, and let F be this set, and compute R using this, we find that R is this, and the class of 1 is equal to the class of 2, which is the set of 1, 2, as you can see by these four, and then the class of 3, oh crap, what the hell did I just do? And the class of 3 is only the set of 3, because 3 is only paired with 3 here. So the set of all equivalence classes are the set of 1, 2, and the set of 3, which is precisely what F is. Keeping this in mind, let's come up with some lemmas first to prove this theorem. The first lemma says that if A is a set and F is a partition of that set, if we let R be the union for X and F of X squared, then R is an equivalence relation on A, and we'll also call R the equivalence relation determined by F. To prove that it's an equivalence relation, we first have to show that it's reflexive. And to do that, let's let X be arbitrary, and let X be in A, and X be in S for some S in F. By definition of R, X is R related to X, since, if X is in S, then X is in S, since R pairs elements that come from the same set in F. So R is reflexive. Now let's suppose that X is in S, S is in F, and X is R related to Y. Then this means X and Y are both in S. So by definition of R, Y's are related to X, since again it pairs elements that are in the same set in F. So R is also symmetric. Now let's suppose that X is R related to Y and Y's are related to Z. Then this means that there exists some S in F such that X, Y, and Z are all in S. So since X and Z are in the same set, that means that X is R related to Z, by definition of R again. So since X, Y, and Z were all arbitrary, this means that R is transitive too. So since R is reflexive, symmetric, and transitive, that must mean that R is an equivalence relation on A. Now that we've proven that lemma, let's move on to our next lemma, which says that, again, if A is a set and F is a partition of that set, let R be the equivalence relation determined by F, which was defined up here as this union. And it claims that if you let big X be in F, and small x be in big X, then the class of small x will be equivalent to big X. So since this is an equality of sets, we can view this as an if and only if. So we can prove this is true if we prove that both are subsets of each other. So for left to right, let's let Y be an arbitrary element of the class of X. Then by definition of the class of X, Y's are related to X. And by the definition of R, Y must be in the same set as X. And so since X is in big X, Y is also in big X. And since Y was arbitrary, that means the class of X is a subset of big X. Now for right to left, it's going to look very similar. We suppose that Y is an arbitrary element of big X. Then this is true if and only if Y's are related to X by definition of R. And Y's are related to X if and only if Y is in the class of X. So here we've shown that since Y is arbitrary, that big X is a subset of the class of X. So since they're both subsets of each other, this means that they're equal to each other, specifically big X and class of X. Now since we have these lemmas, we can use these to help us prove theorem 6 here. And to start the proof, we'll let R be, of course, the equivalence relation determined by F, and by lemma 7, R is an equivalence relation on A. So now if we let X be in A modulo R, by definition of A modulo R, we know that X is the equivalence class of some element X in A. And by lemma 8, all equivalence classes for R will be some set in F. So since X is an equivalence class, X is an F. And since big X is arbitrary, we can generalize this to saying that A modulo R is a subset of F. Now for the right to left implication, we'll assume that X is an arbitrary element of F. Then by lemma 8, X must be the equivalence class of all of its elements. And since all elements in X are elements of A, then X must also be in A modulo R, since it's an equivalence class. So since X was arbitrary, we can generalize this to say that F is a subset of A modulo R. So this means that F is equal to A modulo R, since A modulo R is also a subset of F. And thus we've proven Theorem 6. So from this theorem, it shows that if you start with a partition F on a set A, then define a specific equivalence relation on A, depending on F, you'll get that A modulo R is equal to F. So you start from F and you end up back in F. Well, you might ask, is this true in the other direction? Like if you start with an equivalence relation on a set A, then define this family F as A modulo R. Is the relation determined by A modulo R equal to R? Well, the answer is yes, but I'm not really going to prove that in this video because that would be too long. But intuitively, it involves just the definitions of equivalence classes and A modulo R. So overall, equivalence classes are pretty useful. They allow us to group things together that have something in common. That's really the basis that equivalence classes derive off of. So for last example, we know that we can think of vectors as arrows. And we can think of two vectors being the same as their arrows just having the same direction and the same length. So if we define A to be the set of all arrows and R to be the set of all A, B, and A2 such that A has the same length and direction as B, then not only can we think of vectors as just arrows, but we can think of them as equivalence classes of arrows with respect to R here. And in general, you can kind of think of a group of anything as just an equivalence class of something with respect to some equivalence relation, which is pretty cool. Yeah, bye.